So yeah, so these two resources I recommend highly if you want to learn more about transformers and want to learn how to implement them from scratch. The first link has the code that we will be going through right now, and the second link is a very good description of what the code is and why is it that way. So let's start with the transformers architecture. It's a typical encoder decoder architecture based only on attention. So the task that transformers typically solve is of sequence to sequence, where we want to map an input, let's say x1 to xn, to an output sequence y1 to yn. So the encoder block, which is the left side of the image, uh, encodes the input. The right hand, which is the decoder part, will decode this to an intermediate sequence. Let's call it Z1 to Zn. And finally, we have a linear layer and a softmax, which maps the Z sequence, intermediate sequence to our vocabulary, which we finally map into our output sequence of Y1 to Yn. So let's break down these sub parts and go through them one by one along with code. Yeah, so this is the overall architecture will look something like this in code, where we have our encoder decoder block, the entire two blocks that we saw. The forward function will basically first encode our input and then decode it, and it will give us the intermediate representation, which we can pass on to the generator. The generator is nothing but a simple MLP, which in this case is just one linear layer, which will map the output representation generated from the decoder to our vocabulary, and then we perform a softmax over it to get a probability distribution. So let's talk more about the encoder architecture. So the encoder consists of a multi-head attention. So this is a form of self-attention where each input sequence to the encoder can attend to every other input sequence of the encoder. And yeah, it is followed by a residual connection. So you definitely must have gotten familiar with these in homework too. So we have a residual connection and a layer norm layer. And finally, the output from self-attention and layer norm is passed on to a pointwise feed-forward network. So pointwise feed-forward is basically the same MLP applied to each output of the multi-head attention blocks. So let's say we have 12 multi-head attention blocks, the same MLP will be applied to each of these blocks. Yeah, so the transformers actually consist of stacked attention blocks. So one block is basically the encoder layer, which you can see at the code to the bottom left here. And this consists of the steps that we just discussed. We pass it through self-attention to the pointwise feed forward. And the encoder is on the top on the left. And the one encoder layer, the entire encoder layer will consist of n such blocks. So you can see it where you're making clones of the same layer. And typically the transformer architecture discussed in the paper, attention is all you need, consisted of 6 encoder blocks and 6 decoder blocks. So the n that you see here, this will basically mean it has n blocks, n encoder blocks, one after the other. And yeah, that entirely consists of your encoder. Next, on the decoder side, it's a very similar architecture, but one of the major changes is we have a cross attention block as well. So similar to our encoder, we will pass our decoder inputs through a self attention, and you might have noticed that it says masked multi-head attention here instead of just multi-head attention. So the masking is because we only want the decoder input to attend to all inputs, all decoder inputs that come before it. So we don't want it to look at subsequent outputs, which it does not have at inference time. So when, let's say you're decoding a sentence and you have decoded 3 outputs so far. So for the 4th word, you only want to pay attention to the past 3 words and not the ones that are ahead of it, because of the autoregressive nature. So that's how you'll operate in during inference time as well. Yeah, and the the second attention block that you see here is the cross attention block. So this basically performs cross attention between the decoder hidden state and the encoder hidden states. So that's how you figure out which encoder representations are important for current decoding. And yeah, so that's the second one. And then again, we have the pointwise feed forward layer. Each one of these is followed with a residual connection and layer norm. And once that is done, we can pass it on to our generator, which is a linear layer followed by a softmax. And so one thing that remains is the positional encoding. So because transformers are highly sequential in nature, we want some way to induce a sense of order in between the inputs. So we use a positional encoding layer, which uses something like, which will be discussed in detail further. So the positional encoding basically alters the embeddings of the input embeddings, and so with this alteration, we can ensure that even if two same words occur in the sequence, they will have a separate embedding, which will indicate their position in the word in the entire input sentence. Yeah, so I think next. Yeah, so go ahead. Yeah. So I guess the memory is just the encoder representations that are generated. Yeah. Sorry.
Let me clip it here. Yeah, all right. All right, so now let me address some of the common questions that you guys have asked on actually mostly on Zoom, because the Zoom has saved chat so that we can look at it afterwards. But I think those questions are probably applicable to everyone as well. So the first question, so first of all, on transformer self-attention. So this is a different graph from 11777. To be honest, although the previous graph that we showed is based on the original paper that proposed the transformer self-attention mechanism. However, I think this slide gives a clear idea, at least for me, as to what transformer self-attention is. Remember, it's exactly the same thing as the one you just saw before, and it's exactly the same thing as the one you saw in lecture, just drawn in different ways. So in here, you can see that we have three weight matrices, colored differently. So WQ, WK, and WV. I hope you guys are very familiar with these three matrices, right? They are key, query, and value transform matrices. And although you see multiple copies of those matrices, they are exactly the same, right? They are exactly the same matrix, it's just applied on different tokens. And the end result is that you do a multiplication of the query and key, which will get you the attention energy. And you then apply a softmax layer on top of the attention energy so that you get a you get basically a weight of each value, right? And all the weight sums up to 1 so that you don't modify, you don't increase or decrease the magnitude of the value. And after you get the attention score, basically after applying the softmax, you just apply the attention score on the values that you get, so that that gives you the ultimate hidden representation of each token, right? So here, what I'm describing is just scale dot product attention. And so what is multi-head attention? It's actually not as mysterious as you might have thought. So a single key query value matrix combination defines one attention head. So basically, the one we showed here is a single attention head, right? This is a single attention. And to get multiple attentions, you just need multiple copies of the key, query, and value matrices. That will give you multiple attention heads. And what people usually do is to concatenate the representation we get from all the attention has to become the final hidden representation of each token. And the reason for using multiple attention is not really like the intuition of ensemble, but rather it allows the model to simultaneously attend to the same input sequence in different ways. So for example, I think I have some examples on the right, which is attention maps. So the one on the top is from the first paper that proposed the attention, right? So what they were doing was machine-to-machine, neural machine language translation, right? They're translating between French and English. So this is an attention map, and as you can see, the reason that your attention map is mostly diagonal, which means you might be able to resolve this problem using a CNN, basically using the token and nearby context, and you might get similar performance. However, in this case, where your Europe, the term Europe economic zone, European economic area, is translated in French to in a different order. Basically, it's zone, economic, and European. So in this case, that's where attention shows its prowess, right? The attention is able to grab the correct parts from a different language for this translation. And that's where you cannot that's why you cannot simply replace an attention mechanism with a CNN, even though most of the attention graphs you see might be mostly diagonal. And for multiple attention heights, I think a good example would be the one below, where this is from Vision Transformer, where these different, pans and walks are both attended for presumably image description, and these are actually different, right? These have list on, and these pans have a list off, and they are positioned in a different way. So you might actually need multiple attention hats to attend to different kinds of pans, right? And hats are only differentiated by the different random initialization of their underlying matrices. So your attention hats can actually collapse. So your multiple attention hats may collapse into attending the same thing. There's no way you can prevent it. The only thing you can hope is that by initializing them randomly and by training them properly with enough data, they will eventually learn to attend to different things. And okay, so the second question would be a positional encoding. So let's think about it. What happens without positional encoding? Can anyone give me an answer? I think the answer is actually on the slide. Yeah, right. So you can read it. Essentially, without positional encoding, the model won't be able to distinguish the tokens in different position, right? Because the transformer attends to the entire sequence in one go. It doesn't know if, in the previous example, I say here, whether I came first or like came first, because they are processed parallelly. So you need a positional embedding positional encoding to encode the distance, to encode the position. There are, of course, naive ways of doing this, right? I guess if the first two ways you can think of is, the first way you can think of is just add an index to of the token, right? So you can have an index from 0 to, let's say, 100 for a input length of 100. However, the magnitude of embedding increases over time, increases over the sequence length. So it may actually overpower your underlying tokens representation. So that's bad. So some people said, hey, how about I normalize this value so that I divide this the index by the maximum length of our input, right? So that I get a value between 0 and 1. That seems to have solved the magnitude problem. However, a word at the same index in different length sentences will have different embeddings, right? For example, the second word in a sentence of length 50 would have an embedding of, let's say, 1 over 50, so 0.02. However, if the input length is 100, then your embedding becomes 1 over 100, so 0.01, and that's different. That would be bad for the models to understand where exactly this word is. So that's why we use frequency-based positional encoding. I'm not going to show you the formula. It's all on the lecture slides. right? So at each time t, you get a positional vector that is of the same dimension as the word embedding itself, so that you just add them up, right? You add the positional embedding, so positional encoding to the word embedding. Well, this may sound counterintuitive, but I think in practice, people find that this worked well. This actually worked better than doing concatenation. I guess simply because the positional encoding encodes not a whole lot of information, right, besides the position. And you have a relationship that I think this is what Professor has written in the chat. So I think this is really important. So the relationship between the encoding of t plus big T and pt does not change with the variable t. So basically, that means if you have two words that spaced apart by the big T, the capital T, the relationship between these two does not change. Well, the relative relationship, right, does not change with the absolute location of the first token, essentially. Yeah. And Professor also noted that this series is chaotic. It has a cyclic orbit, but it never exactly repeats, right? You don't want the positional encoding to repeat itself, because otherwise, the model won't be able to distinguish between different positions. Yep. And there's also something called positional embedding. So it just takes the positional encoding to the next level. So your positional encoding has a fixed function that you see in the lecture slides. Positional embeddings are learned, just like the rest of the weight matrices. You have an embedding matrix, positional embedding matrix that learns a good embedding. That's more flexible because neural networks are functional approximators, right? And we're just defining functions for positional encoding. So why not let it learn a better function instead of us defining by ourselves? And in fact, most of these state-of-the-art transformer-based architecture uses positional embedding from the BERT, Robota, and GPT-2. So what this plot shows is a cosine similarity of different positional encoding, positional embeddings. The last one, sinusoid, is the one that it's the positional encoding that we see in the lecture, right? As you can see, for the sinusoid, the similarity is mostly diagonal, means that the encoding is only similar with itself, and it has very little similarity between itself and the other tokens. So other indices. Whereas the state-of-the-art architecture actually has positional embedding that's similar in across different indices in a particular way, right? Right. So what are the benefits of eliminating recurrences? So there are two valid benefits and two invalid ones. The first benefit is massively improved parallelism, because remember, in recurrence, your computation for time step 1 cannot happen without your hidden vector from time step 0, right? So this has to happen sequentially, and so your degree of parallelism is limited to basically the matrix multiplications within each time step. However, with transformer, you can now, because we mentioned you attend to the entire sequence simultaneously, your computation happens simultaneously, right? You can distribute that over multiple GPUs or multiple systems to run. So massively improve parallelism. And there's actually less restrictions on the information available for enrichment. Why do I say so? Because think of it this way. Even if you're using a bidirectional LSTM, what happens at a particular time step is that you have basically two LSTMs going different ways. So at each time step, you will have the information from the hidden vector from 0 to t minus 1. And you have the hidden vector representation from the capital T, which is the sequence length, all the way back to t plus 1, right? These are basically fixed. You cannot choose whether you want this token or not. For example, if the next token is not relevant, you don't really want it. You might want to skip this token and get the other embedding, which may be more meaningful. But you cannot do that in a bidirectional LSTM, even in bidirectional LSTM. But with the transformer, you can definitely do that, because the attention is over the entire sequence. However, transformers does not solve vanishing or exploding gradient, and it also does not solve any bottlenecking issue. Why do I say so? Because the bottlenecking is originates from the older architecture. For example, let's say if you do image captioning, you have a CNN that encodes the image into a single hidden vector, which gets passed into the LSTM that runs over time steps. And in that case, your input to the CNN, sorry, your image input is only the hidden vector at time step 0. That is not ideal. That is of course a bottleneck. However, you can alleviate this by using attention-based model. Remember, attention and transformer are two separate concepts. Yeah, transformer just takes attention to the next level, and basically eliminates the rest of things that's not attention, and propose a model that only uses attention to solve a variety of problems. Yeah, so you don't really eliminate bottleneck when you with the use of transformer. You can also you can do the same with LSTM. In fact, you can do the same in homework 4 part 2 using LSTM with attention. Of course, for homework 2 for part 2, just give you a sneak peek, you can also use transformer. We do not limit the architecture of your choice. And okay, let's do a comparison between RN and transformer. In terms of memory, so LSTM has pretty good memory. So we have a study that shows that you can remember 200 tokens of context on average, and you can sharply distinguish 50 nearby tokens. That means you can distinguish the order that those 50 tokens appear, yeah, in nearby. But transformers basically relies on the input context itself as memory, right? So for BERT, it's actually 384 tokens. So it attends to those, basically the entire sentences at once. So you don't really need memory because your input is already there. But okay, but the attention matrices themselves can also be thought of as memory. This is not what's taught in this class, but that's what's taught in 777. And I think that's a valid point, and that's the exact reason that you need attention masking in the decoder, because you don't want the attention matrix, the weight matrices to give information from the future, right? If the attention matrices does not remember anything, you don't really need the masking. Okay, and let's compare the performance of RN versus transformers for time series prediction. This is interesting because RN is supposed to explicitly model a time series using the hidden vector. However, based on what I read online, transformers can still perform better than RN. So these are the quotes from this particular link, which are, I believe what they were doing is doing a stock market prediction, right? They found the RN to be very difficult to train because the model could not decide what information to remember. And the RN was also not parallelizable, as we discussed, so the training time was slow if you have a lot of data. But however, with transformer, with attention, it enables the network to, well, do something. So these are not technical descriptions, but what they believe was happening to help make better predictions. So yeah, basically, if you have enough data, definitely go ahead with transformers. Right now, that seems to be the state-of-the-art model. And okay, I think I may also talk about mask self-attention, so I don't have to repeat him. Yeah, I just want to remind you that the full encoder context, which is I think the memory that we talked about, is always available. So you always encode the entire input sentence and use them as keys and values when you are decoding. Yeah. Right, okay, that's all for my part. I think now let's hand over time to Gaman, who will be presenting online because he's in Kigali. Right.
Hey, bro. Thanks, Joe. Can you hear me?
Gaman, I think your voice is a little bit low. Do you want to speak up?
Sorry, is it better now?
Okay, wait. I think
Is it better now? Can you hear me?
let me try again. Come on.
Can you hear me now?
Okay, but not here for some reason. Yeah. Come on, can you share the screen?
Yeah, sure. Can you hear me now? Zero, is it working now? Can you hear me?
Gamal, we cannot see your screen.
I'm already sharing my screen actually.
Oh, wait, is he? Oh, no, he's not co-host. Okay, sorry. All right, I think Gamal, you can share your screen.
Oh, sorry. Okay. Yeah, can you see my screen now? Hello.
Wait a minute, where is your
Yeah, we can actually see your screen zoom.
Zero, can you hear me in the room? I think it's working fine on Zoom, but I'm not sure why.
Gamal, are you speaking?
Yeah, I'm speaking now.
Okay, I think we'll just resolve the issue from here. All right, I think Gamal, we should be able to.
Is it working now?
Yes, loud and clear. We'll just make it. Okay, go ahead.
Okay. So we are going to present a few transformer-based models. There are many transformer variants, and generally we can classify the transformer-based architecture into three main categories, right? The encoder, decoder, the encoder only, and the decoder only. So the encoder, decoder are the ones that use the full original transformer architecture. And this is typically used in sequence-to-sequence tasks like machine translation. We also have the encoder-only architectures. So this one they use the encoder part of the original transformer architecture, and the output are utilized as a representation for the input sequence. Sorry. So these ones are actually are used for classification or sequence labeling problems. And finally, we have the decoder only, which those models use the decoder portion of the original transformer architecture. So to talk about encoder only models, we have BERT, Roberta, Big Bird, and others. And here we are going to present BERT, right? So as I said, it's using the encoder portion of the original transformer to derive word and sentence embedding. Now let's look at it a bit more in detail. So the BERT model has two frameworks. There is a pre-training and the fine-tuning parts. The model has been created to make it handle a variety of downstream tasks, right? So during the pre-training, we'll typically pre-train the model on unlabeled sentences. So it can be text extracted from Wikipedia. And here we have a special token. We have two special tokens actually, the CLS token and the SEP token. Here we will have the masked sentence A and the masked sentence B. By masked sentence, I will explain what I mean here. The BERT uses two pre-training objectives. We have the masked language model and the next sentence prediction. So autoregressive models like GPT, they typically take a sentence as input and they try to predict the next word, right? So if we take this sentence, for example, unlabeled sentence A and B per, and we pass in unlabeled sentence to an autoregressive model like GPT, we will expect it to predict the next word, which is A. But BERTs use a masked language model objective. It consists of masking out some of the words in the sequence, in the sentence, right? So we can replace the word sentence by a special mask token and also the word per by a special mask token. And the objective is to predict the masked tokens. And it also used the next sentence prediction token, but not the way it's done in GPT. So the next sentence prediction objective is about you pass in two sentences, sentence A and sentence B. And if sentence B is the next sentence that immediately follows sentence A, this is binary actually. So the output will be a Boolean yes or no, whether sentence B is the sentence that immediately follows sentence A in the document. So that's the pre-training part, and it's typically pre-trained on large data sets. Now we have the fine-tuning part. So as I already mentioned, BERT has been designed to handle a variety of downstream tasks, right? So let's take one simple task. We want to do sentiment analysis. So we have a text as input and we want to classify it in three classes, let's say positive, negative, or neutral. We will pass in the inputs sentence here and we will use this token SEP to stop here, and we will not add anything here because we just need one sentence actually. So depending on the task, the fine-tuning of the way we fine-tune BERTs will be different, right? So in this example, we have, I already mentioned this special CLS token. This CLS token will be the only one column of the BERT model. We will use the output of this, we will use the output of in the CLS token and pass it to a classifier with three output, right? We'll pass it to a softmax after that. So we'll have positive, negative, and neutral. So that's for a classification task. But if we are not doing a classification task, for example, and we are doing something else like part of speech tagging, right? We'll pass the inputs here, and then we'll take all the outputs for all the inputs token. And those outputs are basically the representation that we will pass to another MLP on top of it. So there are many different things we can do during the fine-tuning part. We can even use it for question answering, right? We have the question here and the paragraph in which the question is. And then in that case, we'll consider this section actually of the outputs and use it as a representation of the inputs and use something else on top of it. So yeah, we can use BERT for many different things. And we can use it on a variety of tasks. Now let's talk about decoder-only models. These models rely on the decoder part of the original transformer
reply. Hey, Gaman, we cannot hear you now. Guys, looks like a network issue. Let's wait a few minutes for him to come back online. No, he's off the call. I guess in the meantime, do you guys have any questions?
Yeah, I had one. So when we transform a model, I don't recall the model name, but so actually that was the default model which was shown in the transformer paper.
Sorry, I got some logistic issues. Let me continue. Zoe, can you make me co-host, please?
Okay. Hey, come again.
Yeah, can you make me co-host?
Oh, okay, he's not co-host anymore. Oh, give me a minute. Why can't I give him co-host? Oh, I guess again, you gotta give the co-host from your side because you're the host. He's off again. No, he's back. Sorry. All right. Hey, come on, you should be able to share the screen, right?
Yeah, sure. So yeah, just to recap, I talked about encoder-only models. So I talked about BERTs, and it's mainly about representation. Then we have decoder-only models, and it's they use the decoder part of the original transformer and use an attention mask, so that's each position. At each position, the model can only look at the tokens before the attention heads. And GPT is one of the most famous decoder-only models. So yeah, this is basically it. Now let's just quickly talk about encoder decoder models. We have many encoder decoder models actually. We have the vanilla transformer, we have BART, T5. And one thing to point out is most of those models, either BART and T5, they typically don't add much to the original transformer architecture, but it's mainly about the way the training is done, right? Either by using by training it by using language modeling task where you predict the next word, or by masking out, and some even shuffle the inputs like shuffle the inputs. So this is just the original transformer for an encoder decoder model. We have the multi-head attention blocks. We stack a few of them. So here we have the representation, right? And then we pass the representation to the decoder. And for the decoder, we have the masked multi-head self attention blocks here, so that we cannot see the next words while we cannot we can just see the words up to where we are in the network. So yeah, we also have vision transformers. So in the transformer architecture here, what we are basically passing is we are passing input embeddings, right? And those embeddings are basically vectors. So we can actually split our pictures into patches. So here we have 9 patches, and we just pass them into the transformer encoder. And at the end, we have an MLP head, and we can make classifications. So yeah, apart from that, we have a great variety of transformer variants, and transformers are used for many different domains. We use them for in speech recognition. We use them in multimodal models, where we combine many different things like text and images, right? And you can find many pre-trained transformer models here. Maybe I can open the link. Yeah, and here we have many tasks. So depending on what you want to do, you can load the weights for a pre-trained model and fine-tune them on a downstream task. So yep. Yeah, I think that's pretty much it. Now let's move on to the Q&A. Yeah, Joe, I think you can share your screen now.
Okay, sure. Actually, I mean, right now we don't have any. So right now we just have a question. I think we have a question from the classroom. Let me just share the screen so that I can address the problem. Yeah, I think. Are you asking about this particular slide? GPT. Well, this is not really GPT, but this is basically the vanilla transformer. Well, GPT is basically a variation of it. Go ahead. So you're asking about 3 heads? You mean this part?
Multi-attention, fast, and okay. So in the second part, so the input embeddings which are going in the multi-head attention, and then they are being
In this one?
the left one.
Left one.
Yeah.
This one. Okay.
So the output from this is actually in 3 forms, right? Keys, queries, and values.
Right.
And
right.
the output which is we are considering 2 values from the left one to the right one. This is multi-head attention.
Oh, okay. Okay.
Why are we describing?
Oh, no. Okay, that's a misconception. That's a misconception. So that's why, you know, I recommend this particular. Well, I guess I can show you another thing from okay, let me just use advanced modeling models lecture slides to explain it. I think that actually shows a better has a better diagram. All right, there we go. So sequence to sequence with transformer attention. We're not really discarding those you know. So we have 2 streams coming from the left and 1 stream coming from the right. So we're not really discarding those information because we only have a single stream, which is a hidden representation. What we're simply doing with the decoder is that we transform the encoded vector into keys and values, and we transform the condition. And we use the max self-attention as conditioning, which is the query, right? So for every step we decode, we get the query that we want to use. We want to get basically we want to get information for the next word. So we use a query. And how do we get and from where do we get those information? Basically, those are all from the encoder, right? So the encoder has every hidden context, and those are just transformed into keys and values. So we're not really discarding anything.
Query which comes out from the encoder, that is fed as an
The query does not come from the encoder. In here, this query only comes from the decoder.
Obviously, basically the output. So encoder, decoder, output is then fed as an input again, right?
Encoder, decoder.
That as a thing. And where is that query coming? Because transformer has three outputs, right? Keys, values, and queries. And in the encoder part,
Transformer does not have three outputs. Transformer only has a single output. Well, you have a single hidden vector per token. There are no three outputs.
What you have is you have a vector for each token.
Yep.
Between these three times value because this is self-attention. So equivalent value along the same to pass it into attention. Apply that.
I think Amir, you may want to speak here so that the microphone, Let me okay, I'm just using my laptop's microphone.
Yeah. So so you have the input tokens to your encoder block. So these are repeated 3 times, key, query, and value. Because this is self-attention, all 3 are same. So they pass through the attention block. We get attention weights which are applied to the values, which are in this case the same embeddings. And this is the output of your encoder block before output of the attention block of your encoder. So it's not like 3 outputs. It's the embeddings of all the input tokens, but with attention weights applied. And now these again become your key and value for the cross attention between decoder and encoder. So these become the key value for your decoder. And where do we get the query? The query comes from the decoder's input. So I think the other image, this one. The decoder, the output from decoder self-attention block. Yes. That becomes the query, because now you want to basically, if you remember the sequence, encoder, decoder, 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 decoder,
Which microphone is picking up on words?
I think it's that one.
Oh, okay. So the microphone is picking up stuff. Okay. So let's. Okay. Then let's just keep using the laptop mic.
So if in the sequence encoder decoder architecture that we saw previously, not the transformers ones, we had the key and the values came from the encoder hidden states, and the decoder hidden state was the query. So it's similar to the cross attention.
Oh, is it yours? Why? Let's try this. I should have muted this. Okay, that's the reason. Right, I think right now the room mic.
So
Yeah, so basically the dot product of key values that Zishan had mentioned earlier. So that is done in the multi-head attention of the encoder.
It's done in all three attention. The attention mechanism in itself doesn't change. The only difference is what you are generating attention between. So in the encoder, in the first two blocks in encoder and decoder, it's self-attention. So the key query values are all the same thing. The only difference in decoder is that it's masked attention. We prevent it from attending to tokens coming after it. Because you don't want it to have information from future.
Yeah, yeah.
And the second attention block in the decoder is the cross attention. So here the key and values come from the encoder hidden representation, and the query is the decoder hidden.
Just a quick recap. It looks like I forgot to share this particular slide on screen. Right now, that's why I was sharing the other screen. Right. Yeah. But essentially, I think this is a better diagram. Essentially, your encoder provides a single hidden vector per token, which is only used as keys and values. And your decoder has two transformers. One is used for conditioning, basically provides the query for the self-attention, and then this particular the other decoder decodes the actual word for the next step, which is then fed back to this decoder on the lower right, the transformer on the lower right, to get the new query for the next token. Right. So the decoder is a sequential process, whereas the encoder is parallel.
And yeah.
So I think it is a similar question. So the output of math self-attention is that is a word embedded for each token.
For the
Visualize
decoder.
the word embedding.
For the decoder.
Yeah.
Yes.
And for that example, so the purpose of that architecture is to generate the next word.
Yes.
So the reason why you use the embeddings for the second word is to use that word embedding to generate the next.
Yes. So it's most commonly autoregressive. So basically, the prediction at current time step will depend on what was decoded previously, and also on the encoder.
I think that has always been the case for not just for transformer, but for regular LSTM-based decoder. You also need this kind of, right? Basically, LSTM it happens naturally, where you decode at each time step, and then use a hidden vector and the output from the previous time step to make the next prediction, right?
That's why you don't need to mask anything there because you don't have output on the next time step. But because it's parallel here.
Right. Right. I think any questions on Zoom? Yeah. So apologies for just now. I forgot to share this particular screen. I think right now you should have seen the screen and understood what we were discussing up until now. Yeah. Looks like nothing on Zoom. Right. So let's just let's conclude. All right. Thank you so much for coming. And yeah. Okay.